Sir. It's audible.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. You are audible. Definitely, sir. Definitely. Please start. Sir, good evening, sir. Yes, sir. Yes, sir. Yes, sir. You are audible, sir. Sir, your voice is breaking. Sir. Now it is audible, sir. No, sir. Again gone. Yes, sir. Thank you, sir. Thank you for the kind invitation, and I thank very much Dakshinamurthy sir for the introduction. It's a great pleasure and honor to be to present my insights about the nanotechnology and materials revolution at Sri Siddhaganga College for Women. As an alumni of Siddhaganga College, I feel proud to present my lecture for all the Siddhaganga college staff, students, and all the organizers. I especially thank Marappa sir for the invitation. So, can I start, sir? Can I start this one? Uh, okay, I'll share the screen. Is it, is it visible, sir, my slides?
Yes, sir.
Okay, okay, sir. Uh, so, good afternoon, everyone. I'm Dr. Manjunath from Nitya Institute of Technology. I'm working as a research faculty in Bangalore. Today, I'm going to give a glimpses of materials revolution in the future nanotechnology. So, if we go back for several centuries, we know that like our ancestors were using stones as in like weapons and other all the like lifetime vehicle. This one like all the equipments to lead their life, or like you know about the like a stone age. Like so, currently we reached plastic age currently through a silicon age, and all those in between we across several types of revolutionary materials like iron, steel, then copper, all these things we have seen. So today I'm going to give like a brief the glimpses of the previous things. Let's start from the like a stone age. Like our ancestors, we know that nearly 3.3 million years ago, they were using stones earlier, like with the sharp edges, uh, by to hunt for the to hunt their food material like food materials by killing animals and other things, right? So later on, they they advanced their tools from the stones, and they converted into like some other like tools from the stones. Then later on, they went to the Neolithic revolution. The same like stone tools they also used by advancing them into like for agriculture, pottery, weaving, and other accessories to lead their daily life, right? So now, if you go for the Metal Ages, later on, like we have seen after that, we have seen the kingdoms, different kings, different kingdoms. So they used different metals. When we see the metals already, like we are into the already kingdoms, several old kingdoms. So initially, nearly 5000 BCE, we have seen the copper. Okay, there have been like discovery of like alloys from the copper and making tools, ornaments, and also they lead. Already they started advancing their life when they reached to the copper age. Later on, they went to the bronze age. Already, like in bronze age, they already created bronze by using tin and copper alloys. Even right now, also we are using the bronzes, right, for our daily life. Then later on, they went to the iron age. So development of like iron-based weapons, okay, swords and other things for like to secure like, in the security purpose to secure their kingdom. And in the modern, so currently, if we come to the modern landscape, so we are no more using those alloys and other things. So we started using the composites, nanomaterial composites. You know, we call it as a nanotechnology. So in the present world, we are majorly using the steel. Okay, like we know that the steel industries in all our homes, like we are currently using utensils that they are made up of aluminum and steel majorly, or steel coated. And also in all iron and steel industries, and in many large scale industries also, they're using steel and iron to build the infrastructure like machinery, skyscrapers, bridges, railways, and mass production, and all those things. And also aluminum, since it is lightweight and strong, transforming transportation and construction. You know that aluminum is being widely used because of its lightweight. And currently, we see that apart from all, like we are using mostly polymers. Everybody at every time we are using plastics, right? So in everybody's home, like most of their things or boxes and other things are made of the plastics. Not only them, even outside in the society also we are using plastic and polymers a lot. And silicon, even like nearly 4 to 5 decades we have been using silicon as a major source of material in in industry scale, like especially electronics, microelectronics. If you think about microelectronics, like mobile phones, TV, monitors, and all the displays, we are using silicon as a major source, as the basement material. And also, we are using that in the solar panels for the past 4 to 5 years. But we did not realize that there are better materials available in the society apart from silicon, but it is taking a lot of time to go to the composites by replacing the silicon. Currently, you have seen that Indian government has established the semiconductor industries where they're using where they're replacing microelectronics into by nanoelectronics. That means a 2 nanometer chip they are trying to make. Currently, like it's quite challenging. They already tried to make a 24 nanometer chip, but still it's not into the large scale. But definitely one or the other day soon, we are going to bring the nano electronics into the market. So this is about these are about the materials evolution till now. And what about the future generation materials? If you look at this mainly, nanomaterials will come into the picture. There are several nanomaterials, especially graphene, carbon nanotubes, metal oxides, sulfides, nitrides, phosphides, carbides. There are several materials in the nanomaterials. And smart materials. Smart materials, if you already, we have seen that, like we already, many people are enjoying. If you take the autopilot cars, like simply they are like they give a command to the this one inside the this to the electronics, and they set the destination. Simply they sleep and the car will take them to a destination safely. So those are called smart materials. Also these smart materials have been using in the windows. So if the light is high, so windows will become dark, it will not allow sunlight into the homes. And if the light is lower outside, then it will become like a transparent, so that we can see more light inside the homes. So these are called smart materials. And also sustainable solutions. What are sustainable solutions in our market? So there are nanomaterials based on the bio-based material, bio-based biomaterials, recyclable polymers, plastics, green manufacturing processes, which are addressing the environmental challenges like pollution and other things. In today's scenario, if we look at the scenario across the world, material scientists are developing substances that could redefine civilization that we have seen in previous era, like Stone Age, Iron Age, and Copper Age, all these things. So we have there are still rooms at the bottom, and in the future also we can definitely bring the superconductor in the in place of the present conducting materials, which can bring higher efficiency. And let's look at the nanomaterials. Okay, I'll just give the brief glimpses. Nanomaterials means the materials with at least one of its dimensions should be within nanometer range. That is less than 100 nanometer. That means if we, for students, if you just look into it, it is nearly 10 power minus 9 meter. That is 1000 millionth of meter. That means If you take 1 meter scale, if you cut that into 10 power 9 times, you will get 1 nanometer size particles. Is that possible in reality? Mostly it is not possible, like by mechanical process. Definitely there are possible methods to bring 1 nanometer size materials. Just to understand how small 1 nanometer is, I'll just give you some examples. Like those who are biology students, like we just think about one red blood cell, RBC. One RBC is nearly 7,000 nanometer wide, 7,000 nanometer. And in general, if you look at the water molecule, the diameter of water molecule, one molecule of water, H2O, is zero point 0.3 nanometer across. And human air, if you think about the diameter of human air is 80,000 nanometer wide. So these are the examples how, to understand how small the nanometer is, this one. And if you look at the history of nanometers, are these nanometers very new to us? Definitely not. Actually, several centuries ago, like Romans, they were using materials. Like for example, they have prepared like this cup. You have seen. I've shown you like right side, the green color. When the light is reflected, it looks like a green color. When the light is transmitted, it looks like a orange color or pink color. So these materials, like earlier when they were earlier period, they were not known that these are the nanomaterials, but they already developed. But due to like lack of the technology, they could not identify whether these are nanometers or micromaterials. But definitely they were existing. And why are these nanomaterials different? Because the properties of these nanomaterials are different. What properties? Generally, if we look at the properties, mainly surface area, surface to volume ratio, and quantum confinement effect. These two are the key factors which bring a major changes in the nanomaterials when we reduce the size from micro to nano. So what is quantum confinement effect? Definitely like the wavelength of the nanometer changes and confinement of the particle also changes. And if you look at the types of nanomaterials, like based on morphology, this definitely, these are definitely these are classified into 4 different types. That is zero-dimensional nanomaterials, 1D nanometers, one-dimensional, two-dimensional, and three-dimensional nanomaterials. I'll just explain one by one. Zero-dimensional nanometers means they simply looks like like a spherical particles, or all the sides, length, width, and breadth are in the same size. For example, if it is 1 nanometer diameter, all the sides is 1 nanometer. There will be no change in in the size. And one-dimensional nanometers means only one dimension will be out of nanometer range, that is more than 100 nanometer, and remaining two dimensions will be under the nanometer range. And two-dimensional nanometer means two dimension will be out of nanometer. For example, if you take the length and the width will be different, will be out of nanometer. And if you take the height of the this one will be in within the anyone will be within the nanometer range. Two-dimensional will be out of nanometer range. Three-dimensional. Three-dimensional, all the 3 dimensions, length, width, and breadth will be out of nanometer range in case of size, but they act like they show the similar properties to the nanomaterials. Let's look in detail. Recently, like a couple of years ago, Nobel Prize has been given to the quantum dots technology. So we in quantum dots means like they are they are in the range of 1 to 3 nanometer range. So they looks like a spherical particles dots. They are majorly used in display technologies. Right now we have seen LED, LCD TVs, but in future we are going to get QLED TVs. That means the intensity and the brightness and whatever the quality will be nearly much better than the present technologies. And if you look at the nanoparticles, metal nanoparticles also can be called as the zero-dimensional nanoparticles, and also carbon dots, like you have seen graphene and other things in the carbon materials. But if you look at the carbon dots, they will be less than 5 nanometer diameter. So those are called as zero-dimensional nanometers. They bring a major revolution in the nanotechnology for the future generation, definitely. And if you look at the one-dimensional nanomaterials, as I told earlier, only one dimensional will be out of nanometer range. Especially if we take the examples are nanowires. Okay, there are various types of nanowires have been prepared in one-dimensional category. They've been used in transistors to create transistors, light emitters, optoelectronics, sensors, and other technologies they've used. And if you see the carbon nanotube, they are most popular materials among one-dimensional materials. One-dimensional nanomaterials, carbon nanotubes have been created significant impact among the scientific community. And another kind of nanotubes, like another kind of materials are boron nitrides and nanotubes. These are also creating high impact in the future semiconductor industries. And two-dimensional means, like as I told, that they looks like a sheet form, nano sheets. Any one dimension will be within the nanometer and two will be out of the nanometer. This one, the examples, if you look at, are graphene and nano lasagna, that is called also called as MZenes. The MZenes, boron nitride nanosheets, these three materials have been creating a significant impact in the current industry, nanotechnology, and also they brought a huge revolution among the materials, and they're also going to use in large scale in the future in semiconductor industries. And of course, the graphene has been called as a wonder material, or also called as a black diamond, which exceeds unparalleled electrical conductivity, and its mechanical strength exceeds diamond, and also exceptional thermal properties, like if you take the thermal conductivity. They are used in flexible electronics. In I think you have most of you have seen this watches, like flexible watches or flexible mobiles or transparent mobiles in the social media. So those kind of transparent or flexible wearables, electronic wearables, have been prepared by graphene, by using the graphene material. And nanoscale revolution. Definitely, by seeing all these kind of nanomaterials, zero dimension, 1D or 2D materials, definitely we can bring a revolution among the materials. We have seen the evolution of the human beings. Now we are seeing the revolution in the materials. Nanotechnology definitely evolved beyond the science fiction. Like we say that Superman, Spider-Man, such kind of things. But we can think that by seeing those characters in the movies, they're highly impossible. But even though in materials revolution, many materials have brought unrealistic properties, and definitely we cannot imagine those properties in the nanotechnology revolution. So that is the that's the thing we are going to see in the future, in the near future. And what are the applications of these nanomaterials in the present scenario or in the futuristic this one generation? Mainly, they used in advanced catalysis, for example, in green hydrogen energy, or the conversion of carbon dioxide into clean energy like ethanol, methanol, or formic acid in the industrial process, and heterogeneous catalysis. All these things we can use for the clean energy production. And the next generation energy storage, for example, supercapacitors. We know that already lithium-ion batteries have been into the market. Most of the people are using electric vehicles. Electric vehicles like scooters are there, four-wheelers are there. Also, buses also are running on by batteries, that we have seen. Like 30, 40, 3, 4 decades ago, people thinking that lithium-ion battery is very difficult to bring into the market for large energy sectors like buses and other things. Currently, we have seen that they are being used in the buses, right? So that means they brought a revolution in the energy storage. Smart therapies and diagnostics. So already like many zero-dimensional materials have been used in drug delivery to detect the cancer cells and other bioimaging process in the medical technologies. And super hydrophobic materials. I think we have seen many of you, like if you see the right side image, this is the natural super hydrophobic leaves. When the rain falls on the leaves, just you see the droplets, water droplets, like clearly you can see the 360 degree of the droplet on the surface of the leaf. So that leaf acts as a super hydrophobic. In the same way, even scientists have created several super hydrophobic materials that can be used in paints and textile industries. So if you use in textile industry, definitely like no, we can we don't need to wash the clothes regularly. That means we can save water and energy also. So these play a crucial role also in the future uh, technology revolution, and mainly advancement in materials for energy applications. What kind of energy? So today, like due to geopolitical issues, like we have seen, there is no LPG in the market or shortage of LPG gases in the market, right? So why? So what is the issue for this? Because we are importing crude oil from the abroad, like several countries like Iran, Iraq, Saudi Arabia, Russia, Oman, and other countries were importing, but currently they are like impacted by the war, right? Because of this, import is reduced. We are facing a like crisis. So why don't we generate our own energy in our country? Even though we are most populated, but we are dependent on other countries for energy sector, right? So this is the main issue in this one. Currently, we are realizing the issue of energy crisis. So to overcome this, already government of India is initiated to bring a self-reliant Atmanirbhar energy that is called hydrogen energy. They are investing a lot. They are like working R&D lot on hydrogen energy. How this whether this hydrogen energy will solve our issues in the energy crisis? Definitely, we can resolve the issues with this, because hydrogen is abundantly available we are like in the universe. And second thing, if we are able to convert everything into hydrogen, so definitely like it has a high energy density when compared to other energy sources like LPG. Even compared to CNG, LPG gas, the hydrogen energy nearly 3 to 4 times it gives high energy compared to those highest this one. So definitely, if we bring hydrogen energy into the market, definitely we can resolve the energy crisis issues. Recently, we have done done together with other countries like Israel and other like India. Collaboratively, we have done some developed some materials like vanadium sulfide, tungsten sulfide, and molybdenum sulfide and nanomaterials. We have got like very high energy, hydrogen energy per uh, centimeter energy density in this, that has been published in Energy Applied Materials today. Let's look at the another intelligent and wonder materials that are being used in the present scientific community to bring these we are working a lot to bring these materials into the market. So those materials, if you look, like mainly like many of you are doing research on various kinds of materials, but definitely these materials, whatever I mentioned here, they're going to bring a major revolution in the future technology. Those are called, like, first place is graphene. It will definitely comes into picture. Carbon nanotubes are fullerenes. Hard carbon is being used in lithium-ion batteries. Molybdenum sulfide and tungsten sulfide nanotubes or nanowires are fullerenes. So these materials are going to bring major revolution in many sectors, not one sector. energy applications, painting industries, concrete industries, iron and steel industries, and in many sectors they can do. Let's look at the discovery of these materials. If you look at the carbon fullerenes, was discovered in 1985 by Protos, Smalley and Kerr. Carbon nanotubes was discovered in 1991, Sumio and Izima. And you see, in 1992, tungsten sulfide nanotubes was discovered by Resheftene. Tungsten sulfide fullerenes in 1993 by Resheftene. Molybdenum sulfide fullerenes in 1994 by Resheftene and group. Molybdenum sulfide nanotubes 1995, Resheftene group. Graphene 2004, Andrew Game and Novoslov from University of Manchester. So these are the discovery of these materials. Uh, and if you look at this person, Mildred Drusillus, actually she's the one people call her as a queen of carbon. I think most of you have not known about her. Actually, she did a lot of research on carbon materials, and she gave several concepts, insights into the carbon structures, their properties, and other things. Based on her theories, her concepts, her ideas, people have discovered those carbon materials, such as carbon nanotubes, graphene, whatever it may be. They discovered based on her insights. So that's why, like all the scientific community, call her as a carbon queen. Uh, she laid the foundation for carbon nanotechnology in early 1950s or even earlier. She pioneered techniques to study materials that were just one atom thick and predicted the possibility and characteristics of nanotubes. And she also predicted the possibility and characteristics of nanotubes. And since 1950, she studied the atomic configurations effects on the conductivity of materials in terms of heat and electricity. Her work has been crucial for developing lithium-ion batteries, electronic devices, renewable energy generation, and much more. So to know more about her, we can just go through in YouTube. There are several videos uh, uh, delivered on her discoveries and significant of her work, her research has been displayed in the YouTube. You can check the YouTube videos. And to know more details about that, I have given two references. One is published in Nature in 2017, and she expired in 2017. Uh, Queen of Carbon, Champion of Women in Science. You can go through the article published in 2022. So these two articles tells that what kind of discovery she has done in the carbon chemistry and how they impacted for the discovery of all the other carbon materials. And if you look at the one by one material, that is graphene, most of you know about the graphene. It's a two-dimensional structured materials which consists of single layer of carbon atoms arranged in a hexagonal lattice. All the atoms are in hexagonal lattice. If you look at the properties of a single layer, strength is nearly 200 times stronger than steel, and tensile strength over 100 GPa, gigapascals, and conductivity, exceptional electrical and thermal conductivity surpassing copper and other conductive materials. Flexibility, in case of flexibility, incredible lightweight and flexible. Transparency, it is nearly transparent, transmitting up to 97.7% of light optoelectronic applications. As I told earlier, like in social media, they already created several prototypes based on the graphene, like a flexible, like a transparent mobiles, transparent watches, wrist watches, all those prepared from the graphene. But they use a different percentage, like less than I think 0.1% of graphene will be used in those kind of materials. Hence, it looks like a transparent. And what are the challenges? So why don't we bring graphene into the market? So the main challenge in this also, there are several on the laboratory. It is performing well, and there is no doubt that about its performance and activity and other things. But when we come into the market, there are challenges by bringing graphene into the market. Let's see what are the challenges. The one thing is production method. Currently, graphene is being produced from the Hammers method, by Hammers method from the conversion of graphite into graphene. You know that it consists of it's a complex process which consists of like we take a lot of chemicals and other things to convert into this, and yield will be very less at the end. So because of this issue, it's a major challenge. And cost of production. As I told, the process is complex. We need to produce graphene from graphite. Graphite, like we have to get it by mining the graphite ore. So it's a complex process, and the production cost is very high. And the market in the market, like high quality reduced graphene oxide is very high, and purity, definitely there is impure, and it consists of large amount of functional groups and other things. And so these are the key challenges. If you overcome these challenges, definitely we can bring this material into the market. Let's see application. Already in the laboratory they have tested graphene for various applications. More than 60 applications have been studied and published in the literature. But in the market, this material is being struggled again. Recently, like in 2025, I'll give just a brief, like a few examples. As we know that, in India, or you take in Bangalore especially, if they construct tar roads, how long they stay? Maximum 1 month, 2 months, 3 months, or 6 months, right? So the road gets damaged or broken, or potholes we'll see after a few months, all these things. So these are the key issues in the tar road construction. But UK government, United Kingdom, they have constructed the tar roads by using graphene by mixing graphene into the tar or bitumen, and they observe that the increase, like a significant increase in the durability, and reduces pothole. It forms like film structure, and it provides a smoother driving experience. There will be no much noise on that. So these are the key, the significant factors when we bring into the market. Definitely, already they constructed tar roads from graphene, and they say that nearly 10 times the durability increases when compared to the present or conventional tar roads. Also in US, also they have constructed a national highway, and they're testing its properties in a, in a large scale. And if we look at the graphene concrete is playing a crucial role in the present this one technology. Like recently, in the last few months ago, we have observed that large amount of earthquakes observed in China, Japan, Myanmar, Taiwan, etc. Also in Turkey. So if you just take example of Japan, in Tokyo, nearly they are it is the most populated, one of the most populated cities in the world, and it contains a large number of high-rise buildings, nearly 200 floors. So when earthquake hits Tokyo, definitely they lose a lot of billions or trillions of dollars economy. So because of this issue, so they are trying to bring a different types of concrete, that's called graphene concrete, in place of conventional concrete. The strength of this concrete definitely increases much better than compared to the conventional. And also their experts are seeing that it can sustain up to 9 Richter scale earthquake. Currently we have been hitting with the 4, 5, 6, but definitely they are saying that it can sustain up to 9 Richter scale. That's why even in India, recently I attended a Graphene India conference in Kochi. Like all the construction industries have attended the conference, and they wanted to learn more about the graphene concrete. They were very interested to use graphene into their concrete materials, because even high-rise buildings more than 20, 30 floors, if they want to go, definitely they are planning to use graphene in their concrete material. So that's the interest they have shown to use graphene in their material. So what are the advantages of graphene? As you know that it reduces the cracking, and it enhances the tensile strength, durability, eco-friendliness, cost and efficiency, all these things. And applications like in 3D printing, they are using infrastructure, like as I said that, like in civil engineering, they're using sustainability project, they're using majorly in this concrete. And if you look at the other applications, they're also using anti-ballistic property. Like across the world, I think only US is being has given US, Israel, and only few countries have given like bulletproof jackets to their soldiers, also bulletproof helmets. Only few. In India, they are trying to give. I hope they have given few. So they introduced bulletproof and anti-ballistic property jackets to the soldiers. So this graphene even plays a crucial role in creating anti-ballistic properties in the in the like either in jackets or even helmets. Okay. If you look at the properties, it increases the exceptional strength, like that it will not allow the bullet penetration, and also it reduces the weight of the material. If you are currently, like Kelvar is being used, widely used in bulletproof helmet, it is a polymer and it causes a heavy weight for them. Even soldiers cannot keep the bulletproof helmet on their head for longer time, more than 10-12 hours, because it causes a headache for them, and also it causes like a severe sweat, and their mind will be blocked, and their brain cannot work properly if they keep for longer time. So in place of that, if we use graphene, definitely it reduces the strength, flexibility, energy dissipation, and it enhances the ballistic limits. Also, we can use in body armor, composite materials, energy absorption structures. Let's look at some other applications. Mainly like tire industries. As you know that all the tires are black. Do you know why? Because in car industry, in tires, they mix a huge amount of carbon powder, either activated carbon or the other types of carbons, more than 50%. So that's why it looks black color. The it has say significant uses, because it protects it protects the tire from blasting or bubbling, or from other, and also it enhances the durability of the tire at high temperatures also. So because of this, they're using the carbon powder in that. But still, we are facing some issues like tire blast during summer, especially, because even during summer, the tar will become melting. So during that time, it absorbs more energy. So sometimes even some low quality or unbranded tires get blasted. But in place of carbon powder, if you use graphene, so again the strength of the tire, okay, graphene has, since the graphene has high thermal conductivity, it dissipates the heat energy and it will not be absorbed into the this in the tires, so which enhances the durability of the tire and it increases the strength. And as also, like you have seen in many this Asian Paint is giving advertisement for the graphene paint in many, like if you see the advertisement in between every news channels everywhere, they are giving advertisement. They already bring in graphene paint into the market. It acts as anti-corrosion, antibacterial, and also like hydrophobic, so that the durability of the paint on the walls, either interior or exterior, on the car or wherever it may be, wherever you apply, the strength and the durability increases a lot when you use the graphene as a composite. So likewise, graphene is being used in many nanotechnology industries, also in semiconductor industries. So which is going to be a revolutionary material, one of the revolutionary material for the future generation. And So where do you look at the graphene applications, properties, all these things? You know, Professor Sina Rao has done across the world. He has done enormous amount of research on that, extensive research. He has studied, he has synthesized materials, he studied properties, and explained so many phenomenon concepts of graphene. He published several articles on graphene. He is one of the pioneer across the world in graphene research. Also, he published a couple of books on graphene. You can detail, if you want in detail, you can go through these books. And also, he published one article, you see, like I mentioned here in the Google Scholar, graphene, the new two-dimensional nanomaterial, he published in 2009. Till now, it has reached nearly 4,766 citations for a single article. So it is the most, it is one of the most cited article across the world in the history of this one. So if any of you interested, go through these books and learn more about the graphene, and we can incorporate in our research in the future. And let's look at the economics of graphene. So how economical costs in the market, in the present market, I'm talking about the realistic. Up to 2023, it has nearly $200 million dollars business. It's there. From 2024 to 29, it is expected to be $1 to $3 billion economy it is going to generate. If you look at the cost, graphene, very low cost graphene or low grade graphene, we can say, that is GO or even graphitic oxide, cost is around 20 rupees per gram, and also it will go up to 2 lakhs rupees per gram. So 2 lakh rupees means it is a single layer graphene with no defects. So because of this cost of 2 lakhs, they are unable to bring into the nanotechnology such as electronics. What are the challenges in this? Scalability of high quality monolayer graphene preparation remains expensive, and remains expensive to produce also. It's almost highly impossible to prepare high quality monolayer graphene without any defects in a large scale. So people, like all the scientists, are looking at different methods to prepare this high quality this one, and also twisted graphene single layer. And supply chain risk, like the whole world, China controls more than 70% of the graphite production, prompting efforts to develop mines outside China. Because of this, the cost is not coming down, and also, like as I mentioned earlier, yield is very less. So because of this, these are the key challenges in bringing the graphene into the market. So here, in related graphene, what I thought like a couple of years ago, so why don't we make graphene from a different material? As we know that, like plastic is like rich in carbon source. So why can't we convert that kind of carbon into graphene? This is what I got an idea a couple of years ago. Then we wrote a couple of projects, like we established a startup that is called GFP nanotechnology, which is incubated in our campus, where like we have done extensive research on the conversion of waste plastic into graphene. Currently, like we got successful in R&D, and we are able to produce up to 50 to from 50 to 100 grams of high quality reduced graphene oxide per day in our laboratory. So currently we got successful. Now we are planning to go for a pilot scale. In pilot scale, we have planned to go. We have planned to produce up to 200 kg per day of reduced graphene oxide from plastic waste. It's not a single layer; it is several layers. So we are planning to go for the further functionalization or formulation for the application of various industries. So to bring simply by making the materials and preparing some composites and making some R&D will not be is not enough to bring the material into the market. We need to bring attention among the investors. We need to bring attention among the officials, governments, then users, end users, all these things. To bring that attention, I have written an article like a few months ago and published in Deccan Herald in the state edition to bring this attention uh, on graphene. And another thing is hard carbon. Even hard carbon, yeah, I have hard carbon is it is another form of carbon material. It's a new. Very few people know about the hard carbon. It just emerged like a few years ago, and it has come into the scientific field. It is a unique form of carbon that is characterized by its ability to convert into graphite even at extremely high temperature. The special quality is like graphene. Graphene can be converted back into graphite at certain stages, but this hard carbon will never convert back into graphite. So that is the uniqueness of this carbon material among all the when compared to other materials. Even you can take this to 3000 degrees Celsius, it will never convert back to the. That's the main properties of this. Hence, it is called a non-graphitizable structure because it will not convert back into graphite. Applications, if we see green hydrogen, energy storage, sodium-ion batteries, lithium-ion batteries, all these things. Again, challenges. The challenges are low conductivity compared to graphite and graphene, and variability in performance. 2D metals. There are also some 2D metals which are like in the research we can bring into the market, which can bring a revolution in the future nanotechnology. Those are called like MZINs. We have seen 1T MYS2. These can be prepared by, recently one research group they published one paper in 2025. They can prepare by using the van der Waals squeezing method. It's a new method. We can squeeze several layers. We can remove the van der Waals force, van der Waals spacing, and that will become the metals because they will be in 2D state. And another material, it is called monolayer amorphous carbon, MAC. So it's a new material came into the scientific community. So in this, so each material consists of both amorphous in nature as well as nanocrystalline. If you see here, right side here, a single material consists of some islands of nanocrystalline, some islands of amorphous nature. So this material is nearly 8 times. Currently, graphene is the tougher and the strongest material, but this material even 8 times stronger than graphene. So we can also look into this material. And also currently most of the people are working on 2D, two-dimensional MOS2 nano sheets, right? So what if you convert nano sheets into nanotubes, one-dimensional? As I told earlier, Professor Rasheftine has prepared MOS2 or WS2 nanotubes in 1990s. And if you look at the layer structure has so many disadvantages and less efficiency, if you convert them into one-dimensional structures, so they show better property when compared to the two-dimensional materials. If you look at the side view is a trigonal prismatic. It is a 3-layered structure, two layers of sulfur, and the middle one is a metallic atom. Metal means like either molybdenum or tungsten. If you look at from the top view, it looks like a hexagonal structure. So if you look at some properties, it's bulk MOS2 or WS2 nano sheets is in it's a bilayer. Bilayer means two layers will be there in a unit cell, which has a spatial inversion symmetry. And if you convert 2 layers into 1 layer, so it will be into the non-centrosymmetric or trifold rotational and mirror symmetries will be observed in this. The same thing if we a single layer, if we convert this into a tubular structure, the whole like a list of properties will be changed. Like the symmetry will be into broken inversion symmetry, curvature breaks a mirror and rotational symmetry will be broken, inversion symmetry will be broken, the parallelity or the parallel geometry will become into polar structure. We can see the polarization. These properties will bring like a significant properties in the nanotubes. Recently, my professor from Israel, in collaboration with some research group of China, they've developed one device that is called artificial vision system device from the single nanotube. So this single nanotube acts as like a multifunctional material. That means four different types of functions will be incorporated in a single material. Definitely, like to make this artificial vision system device, we need to incorporate nearly 6 to 7 types of nanomaterials into it. But here, single material is acting as all kinds of like showing all kinds of properties in this. That is called photovoltaic effect and ferroelectricity, chirality, polarization, and also photovoltaics. So what photovoltaic photovoltaic effect will do? It will detect the object or something, and also it memorizes that memory. It will send back to the certain devices, and also it power due to the chirality and polarization. It acts as like power and also processing. Finally, that will command to a certain device to act accordingly. And if you look at the like what it will do, like in artificial vision system, image sensors will be there, image processing, feature extraction, object detection recognition, decision making. And where we can use these artificial vision system devices, like we can use in robotics, autonomous vehicles, medical imaging, security, manufacturing. I'll just give an example. Recently, we have seen like autopilot cars, right? Simply, you will give a command to the car, so it will take your destination. So how it will work? It will have a sensors or camera, so it will see from the camera. Okay, it will detect the object, or it will detect any like vehicles movement or any other things around, and it will tell steering to like if some object comes, it will take steering to take left or right side, or if it needs a brake, it will tell brake to apply a brake. So this kind of system, all the system will be works in a single like device that we have to make. So that is called artificial vision system. And if you look at the properties of the like the structures of the nanotubes, so if you look at in SEM images, they looks like left side WS2 nanotubes, the first one, and below one is MOS2 nanotubes. Right side one high resolution TM images. And here, like invested nanotubes consists of defected nanotubes, left side, number 5 and 6. 7 and 8 are highly crystalline nanotubes. 7 and 8 can be used in the electronics. 5 and 6 type of nanotubes can be used in the energy applications. And as I mentioned earlier, so like I have shown you the structures like a trigonal prismatic. Where can we see this? Because people generally get these structures from by refining X-ray diffraction data, but really in reality also we can observe these structures from TM images. This is the A is the high resolution, high magnification TM image. So this is the highest I have gone. So this is my material. B like I have zoomed into this part. I have taken like this. This can give only some like if you have taken properly. And you have seen here the arrangement of these atoms are like a trigonal prismatic. As I showed earlier, like it is a side view. And if we look at from the top view, it looks like a hexagonal shape. And applications of MOS2 and WS2 nanotubes, green hydrogen, lithium batteries, nanoelectronics, optoelectronics, sensors, lubricants, and also in defense. And he's the person, as I told, like Professor Rashef Tene is the emeritus professor at Weizmann Institute of Science, Israel. He's the first person, is the inventor of MOS2 WS2 nanotubes or MOS2 WS2 nano fluorines. He is my postdoctoral professor. Even I'm a part of MOS2 nanotubes discovery. Other emerging nanomaterials along with these materials like carbon nanotubes, carbon fluorines, amorphous carbon, BCN, HBN, C3 and 4. And if you look at the inorganic materials, MOS2, WS2, fluorines, nanowires, nanotubes, metal carbides. You can look at there are several metal carbides, gallium nitride. Gallium nitride is going to be a boom in the semiconductor industry currently, and also silicon carbides. So I'll just give the brief glimpses of my work, which I did during my PhD and postdoctoral fellow. As you know that preparation of TiO2 generally by hydrothermal and other technique, which generally takes minimum 12 to 24 hours. But here in this technique during my PhD, I just did this TiO2 nanoparticle in just 1 minute by mixing a TaCl4 in the ionic liquid and as well as water. By intermixing this, I got very huge amount of foam within just seconds. That I just did the calcination to remove the ionic liquid, and this got published in Chemistry European Journal as a very important paper. And another kind of materials, as I told, like these materials, like many people are using are using zinc oxide in your research, but zinc oxide has several limitations. It cannot it cannot be used for the visible light applications. Instead of zinc oxide, you can use zinc nitride Zn2NF. So this is one of the materials we created as an alternative material for zinc oxide. And also, instead of mercury oxide, we prepared zinc nitrate fluoride Ag2NF, which has been published in EJIC and also accepted in the cover page. In this, what will happen? The structures of both Ag2NF and HGO are same, but properties are different. So this is what we have shown in this. In the similar way, so as I've shown here, these materials, zinc oxide, cadmium oxide, mercury oxide, TiO2, CDS, CDSC, CDTE. So instead of this, you can use these materials which have similar properties, similar structures, but different properties. And at the end, we need to look at, so what are the material, what are the methods people are using to prepare these kinds of future technology materials. Is like mainly we know that it's a top-down methods and bottom-up methods. Top-down is ball milling, physical vapor deposition, or sputtering, magnetron sputtering, etc. And if you look at the bottom-up methods, okay, everybody is using the same same methods, but they're using a different strategies to prepare different precursor. They change the type of precursor, all the parameters they modify to prepare wonder materials. As you know that these are traditional methods like hydrothermal, solvothermal, combustion methods. So it is very famous combustion method. Sol gel is known. Chemical co-precipitation is known. Hard templating, CVD method or MOCVD, atomic layer deposition. So currently, if you want to prepare a single layer graphene, you need to use the chemical vapor deposition technique. And also electrochemical deposition is there, solid state pyrolysis is there, quartz tube synthesis is there, biological and green methods are there. So these are this one. And what are the characterization we can use for these materials? If we see in this, there are, as we know that many we know, XRD we know, SCM we know, TEM, Raman spectroscopy, atomic force microscopy, AFM, magneton force microscopy, NMR, FTIR, UV we know, like XPS, DLS, zeta potential, Bronner BET, or TGA, DSC, like this. So these are the important techniques that we can adopt in our research to bring high quality publications. Also, we can prove these materials are better for the future nanotechnology applications. At the last, I need to acknowledge my previous professors, like supervisors, mentors, and other people. My PhD supervisor, Professor Ramakrishna Pa, Dr. G. Nagaraju, Professor Jaiton Dupont, Dr. Jackson from Brazil, and my postdoctoral supervisors, like Professor Sienna Rao. I worked a quite long time with him, and my postdoctoral supervisors from Israel. I worked on MOS2 100% yield of one-dimensional MOS2 nanotubes for the artificial vision system, nanotechnology, and energy applications. So with this, I would like to thank all the participants to participate actively in this presentation. And also, I would like to thank organizers, especially Marappa sir, for inviting me to present this lecture. So I will be happy to answer if the questions, if anybody has with related to my presentation. Okay, thank you. Thank you, sir. Thank you. Sure, sir. Sure, sure. Also, they can ask her directly instead of posting, so it will be easy. Uh,
Good evening,
Sir,
sir.
can I stop presenting? Yeah, yeah, ma'am. Yeah, please.
Good evening, sir.
Good evening, madam. Please tell me.
Sir, I'm Dr. Rashmi from Tumkur University. Sir, I wanted to know, can you please give some insight regarding the palladium catalyst which can be used?
Ma'am, palladium, as
You
know, it's
mentioned
like, uh,
you mentioned about the zinc, sir, zinc and zinc oxide.
yes,
So
yes.
whether the gold, silver particles are used for preparation, and how about the gold and palladium as a nanoparticles? Use
Already they
this
are using,
as a
ma'am.
composite material?
Already gold, palladium, they are using already in heterogeneous catalysis.
Yes, sir.
Yeah, many people have prepared and already being used. But gold and platinum, as we know that they are like noble metals, and their availability is way less. So we cannot bring them into into the commercialization part.
Whether they can be used as a both as a conjugates to prepare a nanomaterial, sir?
But madam, where?
Whether both can be used as a composite to the nanomaterials, sir, to
Yes,
prepare a
yes, ma'am. Yeah,
nanomaterial?
yeah, yeah. You can use it as alloy material.
Okay, sir. Okay.
Yes,
So
yes.
I wanted to know one more thing. So like silver can be used, generally silver nanomaterials are used, but when we check the efficacy of the bacterial, antibacterial activity, so definitely there will be showing of this antibacterial efficiency. Is it because of the nanoparticles which is used? Because silver itself is a antibacterial, having antibacterial property. So how better we can differentiate it is because of our compound or because of the metal? Is there any
Actually,
thing?
silver is one of the most highly conductive material already in many in all the pharmaceutical products. Like as you said that antibacterial and other activities, like in sunscreen lotions, in many pharmaceutical industries, they are
Yes,
already
sir.
using the silver nanoparticles. If it is less than 10 nanometer, this one, they show much better antibacterial activity or antifungal activities also. They are already being used in pharmaceutical industries in large scale.
Okay.
Even if you are able to prepare less than 10 nanometer size distribution of silver nanoparticles, there is a huge demand in the market. So they are
So
selling up to like 3
yeah.
lakhs per kg.
Okay. So can you tell me which metal can be selected as the best uh, for selecting for the preparation of nanomaterials, sir?
What nanometer you want to prepare, ma'am?
So using the plant extracts and also or microbial extract.
Plant and microbial extract, like people are using only for like metal nanoparticles preparation, platinum, gold, silver, gold, palladium, like that. But the one thing is, like, if you are able to prepare in a large scale, there will be like a commercial demand,
Okay.
large scale, in a cheap process. And if
Yes,
you
sir.
look at the cost, people accept only silver. Platinum,
Okay, sir.
palladium, and gold, they don't accept because the cost is very high.
Okay, sir. So can we use the oxides of the metals?
Yeah, ma'am. If they show better activity, you can use. But till now, like they have not shown better activity, and oxides, it's difficult to prepare like a uniform size distribution less than 10 nanometer, 10 to 20 nanometer. So that's why people are using like in industry they're using only platinum. If you are able to bring like you can like you can just do like any composites like oxides or other materials
Yes.
because they have like very large scale distribution. There is no narrow size distribution. And narrow size means like 5 to 10 nanometer or 10 to 10 nanometer, 10 to 20 nanometer. So people
Okay.
just prepare randomly, like they will have one will be 5 nanometer and another will be 200 nanometer. So that much long range distribution people will not accept in the market.
Okay, sir.
Okay.
Thank you so much, sir, for valuable information. Thank you.
Ah, Dr. Manjunath, so it was nice talk. Uh, I have,
Hello.
yes, yes.
Oh, yeah, 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 yeah.
So it was nice talk. So I have one question that you are synthesizing this graphene oxide
Yeah.
from plastic, this thing. How they are different from usual from what we get from modified Hammers metal? How they are different, what you are synthesizing?
So in case of properties, material is like our material like RGO show the similar properties when compared to the RGO prepared from the graphitic process like by Hamas method. But
Mhm.
as I told that their process is complex. They have to get it from the graphite. Even graphite, getting graphite is very complex. It causes a lot of environmental issues, mining, other things. And graphite to GO, it will be there, then GO to RGO. So again, that process is very complex and it will be very less. They take a lot, like a minimum, like a single batch of reaction will be, it will take nearly 4 days.
Mhm.
So our process is very quick. Within 2 hours, we will get it the final product, and also we can go for like it is more feasible for large scale production.
Okay. And this carbon, oxygen, and different functional thing, you can control there here also if you
Yes,
want.
yes, yes, yes. Yeah, like we are straight away getting like highly reduced like graphene.
Okay. Nice.
Oxygen ratio is less than 10%, but generally they will have like 30 to 40%. In
Okay.
our case, oxygen percentage is very less.
Okay. Nice, Panja. Thank you.
Thank you, sir. Even thank you, for the invitation for organizing this online workshop.
Thank you, sir.
Yes, sir. Yes, sir. Yes, sir. You are audible, sir.
Will you share some PPTs, sir, from mathematics and from AI tools, research methods? Yes, sir. Those two PPTs are very nice and important to us. So please share them. Sir. Yes, sir. Thank you, sir.
Thank you, sir.